today we're going to look at a couple other trends that we can see on the periodic table. Last time we looked at how we can figure out the size of an atom or the size of an ion. So now we want to think about the trend of ionization energy. And the first thing you need to know about this is know the definition. And there are two definitions that we're going to learn today, one for ionization energy and one for electronegativity. But it's really important that you know the definition, because if you know the definition, it makes the trend really easy to understand. So the first one is first ionization energy, and this is the energy that's needed to knock off that most loosely held electron. So that's the definition for the first ionization energy. If we were to say the second ionization energy, all that we would do is add in the second most loosely held electron, and if it was the third, it would be the third most loosely held. So you don't have this in your notes. This is before we're actually going to write things down in our notes. But if we just wanted to think back about what we talked about last notes, we talked about how distance from the nucleus, effective nuclear charge, shielding, and electron repulsion can affect some different trends. So in this one, we want to think about what factors help to explain the trends in ionization energy in a group. So if you think about what we're comparing here, we've got hydrogen and cesium. So we can see, we look at our periodic table, and hydrogen and cesium, those are going to be, what group is that, hydrogen and cesium? Alkali metals. So we've got our alkali metals, and we can see the difference in both of these, regardless of which one we're looking at, because it's an alkali metal. There's only one valence electron. But which one of these do you think would take more energy to knock off an electron? Is it going to take more energy to grab one from helium or from cesium? What do you think? Helium. Why is that? I'm sorry. Yeah, I'm saying helium, aren't I? Hydrogen. Why is that? Exactly. So it's feeling, it's close to that nucleus. So it is feeling, think about these guys right here as being magnets, and here's your little tiny paper clip. So that paper clip is really attracted to that magnet. It feels that effect. Whereas this paper clip way out here does not feel the effect of these magnets in the middle. There's a couple reasons that we can think about that. So thinking about what we talked about on Friday, one thing, and this was already said, is that it has to do with the distance, right, from the nucleus. So since hydrogen is so close to the nucleus, it's feeling that pull, that nuclear pull. What would be another reason that this one can be knocked off a lot easier? Shielding effect. So we've got all of these core electrons that are here, so that's going to allow it to just be knocked off a little bit more easily. So now if we relate that within a period, so I'm looking and I'm in the second period going from lithium to fluorine, they don't have the same number of electrons. Which one do you think would be easier to knock off? Is that how what factors help to explain the trends? So let's think about easiest to knock off. Would it be easier to knock off one from lithium or one from fluorine? Which one? Lithium. And if we think about, maybe you might even be thinking about the octet rule, that octet rule says that all of those atoms want to have a full outer shell, that they're most stable when they have a full outer shell. Getting rid of one from lithium is going to give it a full outer shell. Here, fluorine wants to gain one, doesn't want to lose one, wants to gain one. So we can relate that in terms of it's not going to be distance from nucleus, and it's not going to be shielding effect, but what does this have to do with? You remember that term? It's effective nuclear charge. So as you move to the right on the periodic table, our effective nuclear charge increased. So we see that these guys are holding on to their electrons a lot tighter than something like lithium. So that might be used to explain it. So now we can get out our pens and sum up everything on the periodic table. We see that the trend, and remember the way this is phrased, it's the energy required to knock off an electron, that most loosely held electron. It's going to take a lot more energy when that electron is close to the nucleus. It's also going to take a lot more energy to grab one from over here, the halogens, where they have a high effective nuclear charge as opposed to the alkali metals. So that's the trend that we see. And so if we were to write some information down, I'm just going to abbreviate. Distance from nucleus, my G stands for group. That affects why we see that trend within a group, you know, as you move up, down. So what we see is that the lower ionization energy, or let's say there is a lower ionization energy as you move down a group because it's easier to knock off because it's so far away from that nucleus. And we also said shielding effect played a role with groups. That greater shielding, as you move down, you've got all of those core electrons in there. So greater shielding as move down, and that's going to mean less nuclear pull. So again, it's going to take less energy to knock it off. And as far as within a period, okay, so effective nuclear charge is going to have an effect on the period, within a period. And what we see here is that as you move to the right, you get your effective nuclear charge is going to be greater, so it's going to hold on to those electrons tighter. So greater as move right, therefore hold on to electrons tighter. And really, we're going to see that electron repulsion doesn't play a big role in this. That played a big role when we were talking about the size of ions, so you might want to go back and review that. Okay, so that's it for first ionization energy. Notice that trend that we're seeing. And then, as always with chemistry, we're going to see that there are lots of exceptions that occur. And we're going to see an exception with beryllium and boron. Remember, we expect it to take more energy to knock off an electron when you move up and to the right. It should take more energy. But instead, what we end up seeing is that it actually takes less energy to grab one from boron than it does from beryllium. So this is a large part of why we learned about electron configuration, so that we can use the electron configuration to help us explain some things that we see. So the trend that we're seeing here is that boron is easier to knock off an electron from. So if you look at your electron configuration for these two, can you kind of see why that is? Where's that electron going to get knocked off of? The P1. So this guy can easily be knocked off. And the reasoning, when removing an electron from beryllium, you're breaking up that from beryllium it's going to be that 2s, and that's going to be really hard to do, to break up an s orbital. So that's why we have that difference. Okay, another exception that we might come across, and that would be with nitrogen and oxygen. So again, according to our rules, it should be harder to grab an electron from oxygen than it would be from nitrogen, but that's not the case. So when we look at these guys, we see that oxygen, how is this different? We've got a 2p3 and a 2p4. What makes it easier to grab from a 2p4? Okay, so I'm hearing the half filled. The half filled has to do with this, right? So here, 2p3 is half filled, so that's pretty stable. 4 out of 6, yeah, that's not as stable, right? So it's easy to grab one of these guys and make it a little bit more stable by being half filled. So by doing that, here we say when removing an electron from nitrogen, you're breaking up a half-filled p orbital, and again, that's going to be pretty hard to do in that case. Okay, so now that was first ionization energies. Here we've got a table just showing some things with some multiple ionization energies. Remember, this would be grabbing a second or a third or a fourth. What you should note, if I just went across, if I looked at carbon, for example, I see to grab one electron takes that much energy. To grab a second one, that much, a third, a fourth. So what you should see is that it's always increasing energy that's required to grab a subsequent electron. Which means, and maybe you can even look at this and see some trends. If I look at and you have a periodic table in front of you. If I look at lithium and think about the fact that that's an alkali metal, it's in group 1, yeah, to grab one's not so bad. But to grab a second, notice the huge jump in energy required. If I look at beryllium, which is an alkaline earth metal, to grab one, not so bad. To grab a second, sorry I covered this up, but not so bad. To grab a third, huge amounts. So looking at your periodic table and thinking about why that is, where are these coming from, these big amounts? Why is that so tough? It's coming from, okay, so it's coming from that change in the energy levels. We have grabbed our valence electrons. Not so tough to do. But when you're trying to grab from here, you're grabbing from those core electrons. It's like grabbing from a noble gas configuration. So here's what you guys have on your paper. We see beryllium as our example. To grab one electron, not so bad. It then takes on the configuration of an alkali metal. To grab a second electron, not so bad. I'm just going to do this. That would go on to an electron configuration of a noble gas. But then to grab that third electron, trying to grab an electron from a noble gas configuration is going to be tough. Takes lots of energy because it's coming from those core electrons. We've already removed those valence electrons. So you should be able to figure out where that big jump is going to be. So this will help you with this. Also, maybe you just want to note on your paper, we said this earlier, but notice that as you continue to grab a second, a third, a fourth, it always increases in energy. Energy. There we go. Okay, so really that's, I think, about all we've got here. It is very hard to remove a core electron. It takes a lot of energy. So now we're ready to move on to another concept. This was ionization energy. And I want to bring back the idea of what our definition was. Ionization energy is the energy required to knock off an electron. Now what we're going to look at is not the energy required, but the tendency or the ability to not lose one, but to gain one. So it's really like we have a double negative, because now it's the ability or tendency to attract those electrons. We used to really make a point of saying that this is when it's bonded to another atom, because we used to talk about something known as electron affinity. We're not going to hold you guys responsible for that, but that's why that's underlined there. So same sort of deal. If we want to think about tendency to attract electrons, fluorine and astatine, we're talking about that same group, right? What's that group called? Fluorine and astatine, they're in what? Halogens. So what factors help to explain trends in electronegativity? Which one do you think would be better at attracting electrons, fluorine or astatine? Fluorine, why? Okay, so, but within a group, remember, this guy has 7 valence electrons and this guy has 7 valence electrons. So it has to do with the proximity to that nucleus. Here, it's so easy to get that paper clip to stick to those magnets because it's so close. Here, it's going to be a little bit harder because it's going to happen, but it's going to be a little bit harder because it's so far away from the nucleus. Not only is it far away, but you've also got the shielding effect of all of these other core electrons. So it's not feeling that charge from the nucleus quite as much. And then if we were to look within a period, what we end up seeing here is that you've got lithium or fluorine, 1 valence electron, 7 valence electrons, 1 full outer shell. So we can see that fluorine is going to be really good at gaining that electron. And again, we can relate that back to effective nuclear charge. So even though we're talking about gaining electrons instead of losing, we see it's the exact same trend because it's kind of like a double negative. Instead of energy required, it's ability to. Instead of losing electrons, it's gaining electrons. So because of that, we see the exact same trend that we saw with ionization energy. And it's going to be a lot of what we've already written down for the other one, but within a group, we could say the distance from nucleus is going to, our electronegativity is going to, well, the distance increases as move down. Therefore, nuclear pull not felt as much. So it's not pulling quite as much. If we go to shielding effect, again, we could say that those electrons shield the valence electrons, the core electrons, maybe we should say that, core electrons shield valence electrons. Therefore, not as strongly attracted to the, not as strongly attracted to those protons. And then within a period, we're looking at effective nuclear charge. And what we're going to say there is just that your effective nuclear charge increases as you move to the right. So effective nuclear charge increases to right, therefore can attract electrons better. You can also kind of relate that to thinking about the octet rule in a full outer shell, having a stable configuration. And electron repulsion does not play a role too much. Finally, the last little thing we want to mention about this is just a little tip. So if you think about this guy right here, there's fluorine. That is going to be your most electronegative element. The noble gases, they don't want to gain or lose electrons, so we really don't even think about them as far as electronegativity comes into play. So fluorine's your most electronegative element. It also has the highest, or a very high ionization energy. You can look at your noble gases for ionization energy, but for electronegativity, we just kind of avoid looking at those. They don't have values to them. So if you were asked what has a greater electronegativity, aluminum or silicon, you would look and you'd say silicon because it's closer to that corner. What has a greater electronegativity? Antimony or bismuth, it would be antimony because it's greater, it's closer to that corner. Okay, so now that brings us to the idea that from this, you should be able to see your trends in electronegativities, and you should be able to figure out the reasons why they have those trends. That's what we just went over. But you will always be given these values. If you ever need them, you would be given those values. And from that, the reason we care about electronegativities, for one reason, is that we can determine bond types based on them. So you do need to know this chart right here, and you need to know it very well. So what this chart tells us is that we can look at electronegativity differences. That's how I will abbreviate electronegativity differences. And it will tell us something about our bond types. Bonds can either be ionic or they can be covalent. And if they're covalent, they can either be nonpolar covalent or they can be polar covalent. And the difference being in let me start by maybe talking about what they're made up of, and then I'll look at the difference between those bond types. So with an ionic compound, what you have is you have a metal and you have a non-metal that are bonded together. But remember, metals are going to lose those electrons, therefore they get that positive charge. Non-metals gain electrons, getting a negative charge. So what happens is you get this transfer of electrons. The metals give up the electrons, the non-metals gain the electrons. So in the process, you get that difference in charge, and they're attracted because of that. And as far as the non-metals go, so these guys are going to be made up of non-metals and non-metals bonding together. And so all they're doing is they are sharing electrons, as opposed to with our ionic, they're transferring electrons. So your nonmetals share electrons, They can either share them equally or they can share them unequally. So if they share them equally, and that's sharing there. So equal sharing would be considered nonpolar covalent, and if it's unequal sharing, it's considered polar covalent. So you can think about poles on a magnet or poles on the earth or something like that. Notice that those are unequal. But if it's nonpolar, then it doesn't have a positive and a negative to it. It's going to be the same on both sides. So that's what we're looking at, and then we want to think about these differences, and you do have to memorize these values. The easiest way, I think, is to put it into a number line like this and just say from 0 to 0.4 to 1.67, and then the highest, it would really be less than 4. The difference that you'd come across would be less than 4, but that would be the very highest right there. So if you think about this, really there's just two numbers that you have to memorize. So what that means, if you're trying to determine electronegativity differences, and the differences are so small between 0 and 0.4, they're sharing them, and they're sharing them very, very equally. There's not much of a difference. So if it's going to be a small difference in electronegativity values, that means it's nonpolar covalent. Equal sharing, they're almost the same. If it's unequal sharing, but it's still not too high of numbers, that's going to be your polar covalent. And if it's so different, then that means they're not even really sharing. It's so different, their electronegativity values are so different because one's actually giving up electrons, the other is gaining electrons, causing that big difference. And that's when you have ionic. So if you look at it maybe in that form, it might be a little bit easier to memorize for you. Okay, and what do we do with this information? Well, if you're given something like sodium chloride, we want to figure out what is the bond type between that sodium atom and that chlorine atom. If we know our electronegativity values, and by the way, you do not memorize this, these values would be given to you, but you can see some overall trends, and you can look at what we were saying, I think off tape, I was talking to the class about how electronegativities of noble gases really do not exist because they don't want to attract electrons. So we just don't even give them values. But as far as bond types go, sodium has a very low electronegativity, doesn't attract electrons very well. Chlorine has a very high electronegativity, so the difference between these, what would that be? What type of bond? Ionic bond. And things aren't going to be 100% ionic or covalent. They're going to have varying degrees, but right now we're just going to be able to classify according to this. So then what if we were to look at oxygen, if you have O2? So you have an oxygen atom and you have another oxygen atom, and they're bonded together. And the electronegativity of oxygen happens to be 3.3. What is going to be your difference in electronegativities? 0. So what is that going to be? Nonpolar covalent. So in other words, if you thought about that diatomic molecule, and don't forget your diatomics, I bring clay for our new house. If you thought about that, you've got an oxygen atom and an oxygen atom. Does one of those guys have a greater share of the electrons? No, it's equal sharing. If we looked at sodium and chlorine, does one of those guys have a greater share? Sure. This piggy right here, the chlorine, those non-metals are very greedy. They grab those electrons. And the sodium, the metals, very easily give them up. So this is not just unequal sharing. It's so unequal that there was even a transfer. Chlorine grabbed those electrons. Sodium gave them up. Okay, so we're going to be able to use these charts. You'll need this for your homework when going through some things. And here's just a little reminder about where metals are and where non-metals are and what's really going on. And you should be able to now consolidate some things that we've learned. We talked about ionization energy and electronegativity increasing in this direction. We talked about the size of an atom or the size of an ion increasing in this direction. So if you're ever given a group of elements and you're asked which one has the greatest radius, which one has the greatest ionization energy, you're either going to be going towards this corner or this corner over here. You are never going to trend to the other corner. So that's just a little tip for you, that it's always going to trend towards one of those. And we're going to sum this all up by talking about reactivity. And with this, you might want to, actually, you know what, I'm not going to do that yet. Let's just answer these questions. It says metals tend to do what with electrons? What do metals do? Lose electrons. And when they lose those negative particles, they become more positive. I'm not really going to explain this right now because but let's just think about what this means. Which metal within a period, where do we find really good metals? Within a period, to the left, to the right? To the where? Left. So within a group, where do we find really good metals? Where are the most active metals? Okay, so within a group, up or down?
Down.
Down. It's going to be down. As you move down, those guys give up those electrons much easier than when you move up. So that's what we see. And then with nonmetals, we see nonmetals tend to, those are the greedy guys, they tend to grab those electrons and form a negative charge. So where might you find a really good active nonmetal within a period? Would it be to the left or the right? The right. And within a group, would it be up or down? Up. So now this is what you guys are going to be doing on your periodic table. You're going to take this and you're going to divide it up just like we had to do with our ions when talking about that. We've got our metals here. We've got our nonmetals here. We're thinking about what makes a really active metal. What's our most active metal? Francium. This guy right here. Why? Well, he's got a really large radius, therefore a low ionization energy. Doesn't take much to flick that electron off. At very low electronegativity, so we can kind of combine all that together and see that that's what makes a really active or reactive metal. And as far as nonmetals go, what's our most active nonmetal? Fluorine, right here. And what makes an active nonmetal is the ability to gain electrons, high electronegativity, high ionization energy. It's going to take a lot to grab one of those off. Really small radius, it's close to the nucleus, etc. So if we were then to put this into terms of metallic character, well, metals are most active in this direction. Nonmetals are most active in this direction. That's your non-metallic character, I guess you could say. So that is it. We are done.